Okay, welcome back to the discussion of tutorial number 3. Okay, problem 2. Problem 2. Okay. Now, what is problem 2? We have to determine whether the following forces are conservative or non-conservative and make a vector sketch of the following forces. So, there are 4 forces given. We will be discussing the second force F2, which is F2 equal to B2 into y square x cap minus x square y cap. Okay, this is a function and b2 is a constant. That's your f2. Why are we discussing second f2 alone? Once we know the mathematics and the physics behind it, you can do f1, f3 and f4. Plus this same function force is repeated in question number 3 also along with f1. And this F2 is showing contradicting results in physics wise in question number 2 and question number 3, and I wants to explain what is the reason behind it. That's the reason I'm discussing F2 alone. So let's look at F2 in question number 2 first, then in the next video we will discuss about the F2 in question number 3. Okay, how will you determine whether a given force is conservative or not? For a conservative force F, it will be always can be always written as a negative gradient of u, where u is your potential energy function. Okay, potential energy function. So energy will be always a scalar quantity. So in the problem number 1 we discussed about the gradient of a scalar quantity will give you a vector quantity. So the force is a vector quantity and u is your energy, and this is how you are getting the conservative forces from potential energy. If you remember in your 11th 12th standard, you know how this relation is obtained. There you had obtained f the potential from potential that du upon dx, negative gradient of du upon dx. You discussed it earlier there, and there the potential energy was a function of x alone and the force was along the x-axis alone. You dealt with only one dimension there. Now since we are dealing with multi-dimension, you have to consider this as the gradient now. Okay, this was along x cap. This is how you did that. So now the gradient will come into picture, and why gradient and all, how the gradient function is defined and all we discussed in the problem number 1. So now I will tell you about some mathematics with respect to the gradient. That let's look take a digression there. Okay, some digression. So let's say we have a function f and this vector and a vector v. This vector v is defined as the as gradient of this function f. So okay, so gradient of f, you know how to write. Gradient of f is equal to del f upon del x, x cap, del f upon del y, y cap, del f upon del z, z cap. This is your vector v. Okay. Now if I take the curl of v, what is curl of v? That is del cross v will give you the curl of v. I will get del cross del f. So what is this del cross del f? If you this is purely mathematical what we are doing. This function is not potential energy. This function is nothing to do with any physics we know. Okay, any physical quantities we know. Okay, this is purely mathematical. So that's why I'm writing mathematical here. This digression is purely mathematical. So this mathematical digression we are going to use in the physics discussion above. So if you do this, what you find is take the determinant of this one, x cap, y cap, z cap. So you know what is this del operator? This del operator is del upon del x into x cap, then plus del upon del y into y cap, then del upon del z into z cap. This is your gradient. So sorry, the del operator. So you can write from here what is this del each quantities here, del upon del x, del upon del y, del upon del z, and from here you can write the quantities of v, this area, this part or v, that is del f upon del x, del f upon del y, del f upon del z. Now I'm opening the determinant. I'm doing it only for x cap, and I will show you how it is vanishing. In the similar way, y cap and z cap also will vanish. So let's see how is it. So open for x cap alone, del upon del y, that is this one, cross this one into this one, that is del f upon del z, minus now this quantity into this quantity, that is del upon del z into del f upon del y, plus the quantities of y cap and whatever coming, and quantities of z cap and whatever coming. So this both quantity will follow what is happening here. You see, this both are same, right? This just you can interchange in a partial differential equation. So which difference in a partial differentiation, so this quantity vanishes. In a similar way, this quantity also will vanish. In a similar way, this quantity also will vanish, which means this curl of this vector is equal to 0. This lets me to give you a identity or a kind of a definition, that not a definition, like a mathematical identity, that the curl of any gradient will always equal to 0. Curl of any gradient will always vanish. Okay, vanish means it's equal to 0. Which means if I take the curl of this function, it also has to vanish, because f is the gradient of u, right? Which means I am going to write our if I am going to take the curl of f, okay, which is a curl of a gradient of u, this has to vanish, right? If I am getting this equal to 0, it is a conservative force, okay, because you know conservative force can be represented as a negative gradient of f, the scalar function. If it is not equal to 0, then it is not a conservative force. So remember this one. So this is coming purely mathematical, okay, purely mathematical. If this force can be represented as a gradient of the scalar function, it has to vanish if you are taking the curl. It's a purely mathematical statement, okay. So you know how to find out force is conservative or not mathematically. So look, our case, what about this curl of our given force, okay, F2, what it will be. Let's see what is the curl of this one. So if I take the curl del cross, okay, let me remove this cross hasn't come properly. So del cross, what we have is y square x cap minus x square y cap. Take the curl of it just the same way we did earlier, put it in the determinant. So x cap, y cap and z cap, there is del upon del x, del upon del y, del upon del z. Now you have for x cap, that is y square, for y cap, that is minus x square, then for z cap 0. So now if you open this, if you take the expand this determinant, the answer you will get will be equal to minus of 2b2 into x plus y, which is not equal to 0, which will be equal to 0 at x equal to 0 and y equal to 0, but that doesn't mean it's equal to 0 everywhere. It has to vanish globally. Okay, this is not vanishing globally, which means F2 is not a conservative force. Okay, so this is the proof for that F2 is not a conservative force. Now, as a extension to this discussion, since we already discussed about conservative force, let's talk about this conservative forces a little more. So F now we can write as delta gradient del of u, right? So work done by this force will be equal to negative integral of a to b between a and b I'm talking about. So F dot dl, this is the work done. So which is equal to negative of a to b minus del u dot dl. Okay, negative and negative cancels. What I have is a to b del u dot dl. We know what is this del u dot dl and what is dl is also. So I am doing the work along this path, and this dl is the small, infinitesimally small distance I am moving. Okay, so now you know what is this thing is from our discussion of problem number 1, that any gradient dot dl is equal to du, right? This we already discussed this. So this has to be equal to a to b into du, which is simply equal to u of b minus u of a, which means this work is a position dependent quantity, right? It's nothing to do with the path you take. So if you which means if you are following different paths along this a to b, like if you are going this way or this way or if you turn around all this place and go back, all will give you the same work. The quantity has to be position dependent for a conservative force. Okay, for non-conservative force, it will be that work has a problem, that will not come this way because there will be dissipation, right? For example, friction. Due to friction, what happens? Energy dissipates. So this is not applicable. But for a conservative force, this is true. Now what will happen? Instead of I am going to A to B, I am going to A to A itself. For example, now I am taking this quantity from A and I am roaming around and coming back to B. To A itself, that is A equal to B. Okay, that's the case, or B equal to A. So what will happen? Such a work is equal to A itself, right? But it's not simply you are standing there, but you are going around it, right? So I'm putting it this round here, which means closed integral. That's like you are started from some place, went through all the path around and came back to the original position. It's like closed one. So this is a closed loop integral or path integral, closed. So that is f dot dl. This has to be equal to 0. Why is it equal to 0? You see that it is a position depending one here. So this will go to 0, right? This is simply equal to u of a minus u of a, which is equal to 0. So if the loop closed integral f dot dl vanishes equal to 0, this is only for conservative forces. Okay, conservative force property. Just follow this. Okay, this is forces follow this, not follow this. Okay, fine. But if this is not equal to 0, f dot dl is not equal to 0 for non-conservative forces. This for non-conservative forces, this won't be equal to 0. Okay. So now the question is, for this, if any force you get, if you put this one in the closed integral and if you get equal to 0, whether it is a conservative force or not conservative force, for conservative forces, if you take this closed integral, it will be equal to 0. Even then, the best way to check whether a force is conservative force or not is actually taking the curl itself. But I am discussing this here for the purpose of discussion in the question number 3. We have some little more further discussion will be there. So this property will be followed by any conservative force. So adding to this, I will make a small further digression. This will be useful for your second semester, and without proof, I am saying that there is a relation, mathematical relation between this curl of f and this closed integral. That relation is simply that if I take the surface integral of curl of f, surface integral means this is the two-dimensional integral. Okay, this you will learn in your second integral, so don't worry about this one. And there is a small surface. Okay, surface. This is and this force field is passing through the surface. Okay, let us consider that means this force field is passing through the surface. And I am considering a small area dA here, okay, and I integrate it to all over the space. That is the curl of f dot dA. I am integrating through all of this space. So what I am going to get is that it is equal to the closed integral of f dot dA. You see, there is a relation now between this curl of f and f dot dA. I just wanted to show you with this relation. This is called Stokes theorem. Stokes theorem, which you are not familiar now. You will learn about it in the second semester in PH102. Okay, in detail, and the proof and all it is there. But since I discussed about this this part of the conservative force, I just wanted to show you how this curl of f and this f dot dl are related there. Okay. So let's see what will happen in the question number 3 regarding the force F2, and work out this problem yourself once more and come to the question number 3. Before ending this video, let me draw the plot the sketch also. So the sketch will be like this. This is the x and y coordinates. Okay. So now this is your x-axis and y-axis. Now you have to find out what is the force here. Okay, so let's see what are the force here. So let's first look at what is the magnitude of magnitude wise and the direction wise, how it will come. Let me take a different color. Okay, now when it is y equal to 0, x equal to 0 and y equal to 0, the x values we have for positive x you have the force field to be some negative value there, you can see, and also for negative x also that force has a negative vector. Force is a negative vector with some, you just say, let's see, this is the magnitude of it. Okay, when x equal to 0 and y equal to positive, it has some value like this and some value like this. So now each point when you come, you will see there will be values, like for example here it will be like this, here it will be like this, here it will be like this. Now this, here it will be like this, and here it will be like this, here it will be like this, here it will be like this. All the places you can find it out by taking for all the values. So now you can write it's like a circular shape there. So each place there will be force has some value like this. It slowly turns and becomes like that. This force is like this. It turns around, it goes around. Okay, on the space. So this is the y-x axis. So this is how your force is there. So this is the sketch of F2. In the similar way, you can find out the sketch of rest of the forces also. Now let's discuss the problem 3 in next video. Thank you for watching this solutions, and try to do yourself and let me know if there is any problem in the comment section.